In this video, we're going to prove an interesting theorem about how the center of a group relates to the group. It's called the G mod Z of G theorem, and here's how it goes. So the theorem statement is this. Theorem: if G is a group, and Z of G, this is of course the center of G, and let's just write the definition here, center of G, which is the set of all G belonging to the group, such that Gx equals Xg for all X in the group. So in other words, it's the set of all group elements that commute with everything. And I think we've shown before that that's a subgroup. All right, so if G is a group and Z of G is the center of G, and G mod Z of G is cyclic, then in fact, G mod Z of G is trivial, which actually will end up meaning that G is abelian. Okay, first let's make the connection that we can readily make here. So why is it the case that saying G mod Z of G is trivial is the same as saying that G is abelian? So I'm claiming that these are two equivalent statements here. And even before we address that, we should probably address why we can even do any of this in the first place. In other words, why can we take the quotient of Z mod Z of G? So for that to happen, we need Z of G to be normal. And the reason that that's true is because for any G in the group and any, let's call it Z, in the center, we have GZ G inverse, the result of conjugating Z with G, is equal to, well, Z is in the center, so I can commute it with anything. So I can move that over. I can commute it with G and get Z, G, G inverse, which works out to just Z, okay, which does belong to the center. Okay, so the reason that the center is normal is because I can conjugate any element of the center, any element of the center, with any element of the group, and I get something that is still in the subgroup, okay, still in the center. So because I can do that, that means that the center of G is always a normal subgroup of G. Okay, but anyway, why is it true that G mod Z of G being trivial implies that G is abelian, and vice versa? All right, so for that, so why are these equivalent? Well, if G mod Z of G is trivial, what it means to be trivial is that it's the group consisting of just one element. So the order of this is just one. There's only one element there. Well, remember, the elements of G mod Z of G are cosets of the center. So this means there's only one coset, only one left coset of the center of G. And if there's only one left coset, well, that coset has to be the entire group, because the cosets do have to make up the entire group G. Okay, but if you have one coset and it's the entire group, that coset's going to be the subgroup itself. So that means that Z of G has to be the entire group. Okay, so that means that G's center is all of G. So every element of G commutes with everything. So that means G is abelian. And you could also run this argument the other way. If G is abelian, then that means that the center of G is just all of G. And then when you start taking cosets of the center of G, well, there's just going to be the one, because that subgroup is the entire group, which means that G mod Z of G is going to be a trivial group. Okay, so this really is equivalence here. So that's not what we came to prove. It's just I felt that that was an important thing to point out. If we're going to show that G mod Z of G is trivial, and really all that that means is that G is abelian, we ought to say that, and we ought to say why that's true. Okay, so anyway, what we're going to prove in this video is that if G mod the center of G is cyclic, then it has to be the trivial cyclic group. It can't be some other cyclic group like the integers or like Z mod P. It can only be the cyclic group consisting of one element, and when that's true, G is abelian. All right, so let's come over here and let's see if we can do the proof. All right, I'm going to switch colors. So this will be the proof of the G mod Z of G theorem. Yes. Okay, so let's assume that G mod Z of G is cyclic. What does that mean? What does it mean for G mod Z of G to be cyclic? Well, as always, that means that there is some element of this group, some element of G mod Z of G, that generates the entire group by taking powers. All right, but what are elements of this? What do elements of this look like? They are cosets of the center. Now, just for notational efficiency here, I'm going to say let's let Z equal Z of G, just so we don't have to write Z of G over and over. So capital Z will represent the center throughout this proof. So then, because G mod Z of G is cyclic, there must be some element, a coset of Z, which we'll call AZ, such that the entire group, the quotient group G mod Z, is equal to the cyclic subgroup generated by the coset AZ, which, just as a reminder, I'll write down that that's equal to the set of all powers of AZ. So let's call that AZ to the K, where K is an integer. Okay, and I might even write that a little bit differently, because what does it mean to take AZ to the K? Well, if I take AZ squared, that's the same as AZ times AZ. And remember, the group operation on cosets is I can just take these two elements and jam them together. So that's going to be A squared Z. The fact that Z is normal lets me do that. And then AZ cubed would be A squared Z times another AZ. And, well, I can just jam those together and get A cubed Z. So in general, this is really the set of all A to the K Z, such that K belongs to the integers. So now we're going to embark upon the following ambitious quest. And I'm even going to call it an ambitious quest. The quest is we're going to prove directly that G is abelian. That's what we're going to do. We're going to prove that G is abelian. And here's how it's going to go. Okay, well, suppose that X and Y belong to G. So suppose I have any two elements of G. All right, we will show that xy equals yx. All right, so here's where having our cosets listed out is really going to help us, because we know that every coset of G is one of these, and that's because we knew that G mod Z is cyclic. We know that every coset looks like A to the K times Z, the center, for some integer K. All right, so because that is true, and because we know that the cosets make up all of G, and I'm just going to make a note of that here. So the cosets, these make up all of G. Okay, and that's just because we know that cosets partition a group. So because we know all of that, here's what we know. We know X has to belong to A to the K times Z, that coset for some K. And we also know that Y must belong to A to the L times Z for some L. And because we know that, we can also say the following. So we know that X can be written as A to the K times some element of the center, which we'll call Z sub X, for some Z sub X in the center. And also, Y is equal to A to the L times ZY. for some zy in the center. Okay, so then what do we know? So then x times y, that's equal to a to the k zx times a to the l zy. And we also know that yx is equal to a to the l zy times a to the k zx. And we want to show these are equal. But now I claim that we have everything that we need to do that here. We have the tools right at our fingertips. And that's because I can take this first representation, a to the k z sub x, a to the l z sub y, and I can move things around. Anything with a z is in the center. Anything with a z can commute with anything I want it to commute with. So for example, a to the k times zx times a to the l times zy, that's the same as a to the k, a to the l, zx, zy, which is a to the k plus l, zx, zy. And also, yx is equal to, well, that's a to the l, zy, a to the k, zx. But I can move that zy over to the right past the a to the k and get a to the l, a to the k, zy, zx. All right, so, well, the z elements, those are all in the center, so I can move those past each other. I can just commute the two on the right. And also that part on the left is a to the l times a to the k. That's the same as a to the k plus l. I mean, I could have said a to the l plus k, but l plus k is the same as k plus l. It's just integer addition. So that's the same thing. These are the same, xy, xy is equal to yx. So therefore, since that worked for any elements of G, G is abelian. That deserves an exclamation mark. Maybe even two of them. Ha! So that means we're done. We've shown that G is abelian. That's exactly what we wanted to show. So let's go back to our theorem statement here, because there's something mysterious about all of this. If I was just going to show that G is abelian the whole time, then why bother with showing, or why bother with stating this whole thing in the theorem statement about how G mod Z of G is trivial? Because that seems like a very complicated way of saying that. The reason we do that, like I could have just said, if G is a group and Z is the center of G and G mod Z is cyclic, then G is abelian. And I think maybe even the book does that. But the reason I wanted to state the theorem this way is, like, now that I've got you interested in G mod Z of G and I'm talking about it being cyclic, I kind of wanted to clarify that G mod Z of G couldn't be just any old cyclic group. It couldn't be Z mod P, for example. It ends up having to be trivial. I just feel like that's part of having a complete theorem statement, is you don't leave those possibilities out there in the ether that aren't actually possible. But really what we showed is that G is abelian, and that's the same as showing that G mod Z is trivial. Another thing I would mention is that we very rarely use the theorem in this precise form. What we often do is we use the theorem in contrapositive form, which is to say, so the contrapositive is, if G is not abelian, then G mod Z of G is not cyclic. And I think we'll use that at some point to classify groups of certain orders. Like, for example, this is a very useful thing to have around when you're classifying groups of order p cubed, because it is possible to have a group of order a prime number cubed that is not abelian, but we will show later on that it has to have a non-trivial center for reasons I haven't disclosed yet. And given that that's the case, not just anything can be the center. It has to be non-trivial, but it also can't have order p squared, because then you'd have G mod Z of G would have order p cubed divided by p squared, which would be p, which would force it to be cyclic and not trivial. So anyway, more on that in just a bit. And finally, one more thing that I just find mystifying about this theorem. We showed that if G mod the center is cyclic, then G is abelian. It is not enough to know that G mod Z of G is abelian. Try doing this whole argument just assuming that G mod Z is abelian, because if you're like me, you will think, surely that must be something we could do, because really all of this counted on being able to move things past each other, and if you have abelian, you ought to be able to do that. But it turns out the argument does not work. The argument will not run the same way, and in fact, the theorem is not true. G mod Z can be abelian, and you can have a non-abelian G. So anyway, those are some interesting things. As you can tell, I'm very excited about this theorem. I hope that I've managed to convey a little bit of that excitement in this video.